talk on a current carrying loop. Say for example, I'll consider this as the magnetic field. Let me write this as magnetic field. And let me assume that I'm having a coil. Say, let me assume this is the coil, a rectangular coil. Say it is something like this. Okay, let me assume that this is the direction of current, or say maybe this is the direction of current is going in this way, here, here, and here. I'll assume that this angle made by the breadth of, say, I can say that this is the breadth of the coil, this is the breadth of the coil, and this is the length of the coil. So that means if I have to write it as area, that will be length into breadth. And we already know that if a current carrying conductor is placed in the magnetic field, so in magnetic field, the force experienced by a current carrying conductor, that is given by I, L, and B. That's the force. Actually it is I into L into B into sine of theta, where theta is angle between say B and the magnetic field. B means the breadth of the conductor or length of the conductor at that point. So you'll say breadth is the angle. So if you want to show that angle, that will be somewhere here. This will be that angle, theta. Now, so I know that this is the expression for force, and any conductor, say for example, if you're taking length, then you'll write length, and if you're taking angle, say breadth for a conductor, then you'll write, instead of L, you'll write breadth. Okay, so what I'll do is that I'll find out first what are the forces on different segments, because each conductor could be thought of as consists of four segments: this breadth, and this length, and this length. So I'll find out force on breadth and force on these two lengths, two breadths and two lengths, and from that I'll see what will happen. So therefore what I'm doing is that I'm going to say find out force. Say for example, if I'll consider here this breadth, breadth is making an angle. Say if I'll show you that angle. Suppose I'm taking one more line, and this is the angle theta that is making with this. It was making an angle theta with it. So angle theta it was making with the magnetic field. Same is here, making an angle theta. So therefore if I'll see, because breadth is making an angle theta, so I'll write therefore force on one of the breadths. There are two breadths, one is this breadth and other one is this breadth. So I'll find out force on the F2. Only thing is, I'll remember that they are having current in the opposite direction. In one, current is going this way, and in the other, the current is coming in the reverse direction. So I'll write it here. So I'll write force on breadth. Breadth 1. Force on breadth 1. There are two breadths. So that means I'm having this breadth here over here. And this is magnetic field. And this was angle theta. This was one of the breadths. So if current was going in this way, and this is angle theta, this is magnetic field. So I'll write force will be F is equal to I L. Instead of L, I'll write this breadth into B into sine of theta. Theta is angle between this breadth and magnetic field. And as long as this coil is there, this breadth is there, because if it changes angle, it will be in this way, and therefore on the other breadth, so say for example this is forced on one breadth, I'll call it as F1, and force on the opposite breadth, that will be equal to I B B sine of theta. Only thing is that on one breadth it will be directed either upwards. So say for example if it is directed downwards, on the other breadth it may be working upwards. Only sine is there and they are along the same line. Say for example if I'm taking one more breadth over here, I'm taking one more breadth over here. This is magnetic field. This is one more breadth. And that breadth is having current in the opposite direction. One is having one direction, other is having current in the opposite direction. So that means that will also experience a force in this magnetic field, but that will be directed upwards. So therefore these fields, these two forces, they are acting in the opposite direction. So therefore this F1 and F2, they are equal, opposite in direction. So therefore F1 plus F2, so there's some force is zero because they're lying or acting along the same line. So that means we have been able to find out force on these two conductors, on this and this. Say this conductor, I'll call this as conductor 1 and I'll call this as conductor 2. I've been able to find out force on 1 and 2 and they are cancelling out each other. Let me come to the other conductors. Let me call this as conductor 3 and this as conductor 4. I'll call this as conductor 3 and conductor 4. I'll find out now force on conductor 3. So for that I'm taking over here, I'll move on to conductor 3. I'll show you the magnetic field. So मेरे पास ये conductor था, this was magnetic field, it was acting in this way, it was in this way, and you were having those conductors, say conductor that was in this way. If I'm showing you the outline of the entire coil, that was something like this. So I'm trying to find out now force on this third and fourth. I'll call this as 3 and I'll call this as 4. I'll find out force on third and fourth. So if I'm concentrating on third, current is going in this way and magnetic field is always having angle 90 here. If say for example coil is rotating also, coil is moving to some other position also, if is supposed to rotate over this axis, then also the length 3, that will be perpendicular to the magnetic field. And I'll write therefore force 3, that will be equal to I, and we know that we have called this length L, and B is the magnetic field, and sine of 90. And similarly, force on 3. Force on 3. If I want to find out the direction of this force, say for example, I have got, I'll write F3 is equal, I have to find out what is the direction of current that is going up, that is going vertically up. So that means I'll write I, L, B, then I'll write direction of L. L is same as direction of current. That current is moving up, so I'll write that as J. And आपका जो magnetic field है, that is on, magnetic field is on x-axis, so I'll write that as I. So if you'll, you know that earlier you might have be aware that I cross J cross K. If you'll do it this way, I cross J, that's equal to K, J cross K, that's equal to, J cross K is equal to I, K cross J, that's equal to J. So that means we already know that from cross product of vectors. So here you have got J cross I, J cross I. So that means it is going this opposite to this. So therefore you'll write it as K but with a negative direction. So therefore you'll write force F3 is equal to I, L, B, but the direction is K, negative K. So therefore negative K means it's going into the plane of the board. Is going it's going into the plane of the board, so I'm writing that as minus K. So that therefore if I have to show that force, say I'll show it using, let me use a different color to show you that. So that is going in this way. This is, say for example, this is going into the board, and this force is I, L, B, and direction is K, that means going into the board. Now in the same way, if I'll find out this force on conductor 4, I'll find out force on conductor 4. 4 is this conductor, so I'll write force on conductor 4, F4 is equal to, that will again, because इसमें करंट की डायरेक्शन ऐसे है, पहले करंट यहाँ से गई थी, then it came down. So that means there is only one change. The direction of current is, earlier it was in the J direction, now it will be minus J direction. So I'll write I, L, B, and direction is J minus J, current की direction minus J. Here you are taking the direction of length same as the direction of current. So therefore this will be J cross, the magnetic field was in the I direction initially also. So therefore this can be written as this. And if you'll find out finally what happens to the force as per this rule, so therefore you'll get F4 is equal to I, L, B, and then this is, you can also write it as I cross J, I cross J, because if you have A cross B, you can write that as minus B cross A also. So that's what I have done here. So I cross J, and you know that I cross J as per uh, this cross product of vector I cross J, that's equal to K. So this time you'll get it as K. So therefore you'll write your force F4, that's equal to I, L, B into K. Now what does it K mean on this, in this figure? K means that force is coming out. Force is coming out this way. out of the paper. Here it is going into the paper. So in order to see that what will be its effect, because these are two forces, one is going into the paper, other is coming out of the paper, and they are separated by a perpendicular distance. They are not along the same line, so therefore they are going to produce a torque. In order to see that torque, what I'm going to see is I'll take a different view of this coil. Say for example, I'll try to see it on this side. Say suppose a person is seeing it on this side, so his view will be something like this. I'll draw that here. So if I'll show you the perpendicular view of this, तो ये आपके पास I'm taking this as breadth, ये breadth of the conductor, this is breadth of the conductor, and actually length was in this way. I'm not going to show it in this because I am focusing on this. And you know that magnetic field was, I'm showing it here, magnetic field that was in this way, I की डायरेक्शन में था, ये B था, ये थीटा था, एंगल था, एंड ये लेंथ में अभी कंसंट्रेट नहीं कर रहा हूँ, बट मुझे पता है कि एक लेंथ पे जो फोर्स लग रहा था दैट वाज गोइंग इनटू, and on the other length the force was coming out, the force was that was coming out, वो बाहर आ रहा था शीट से. So therefore if I'll draw this, you can see that the two forces, this was I L B, and this was in the direction of minus K, and this is also I L B, but it's in the direction of plus K. This is in the direction is coming out, and the two forces, if you want to see what is the separation between them, say for example if this is breadth, then this will be B, this is theta, this 2 will be theta, so therefore this will be B cos of theta. And we have torque because you have got two forces separated by a certain perpendicular distance. In that case we say that it is acting by a torque. A torque is acting, you can write torque is equal to the force into perpendicular distance. Force is I L B. There are actually two forces into I L B, that's the force, into perpendicular distance between two forces, that is B cos of theta. Now length into breadth, if you'll see, what is that? So torque is equal to I length into breadth, that's area, into B into cos of theta. Now if I'll, this is actually expression for the torque. Now if I'll move back to my original diagram, the diagram was something like this, the first diagram. In the first diagram, so this was theta, and अगर मैं यहाँ पे if I'll want to find out the direction of area, so what I'll do is that I'll take a different say a color, maybe like this, and I'll represent that area by this. So that means area will be something like this. This is area vector, and this total angle will be 90. This total angle will be 90. So that means this angle is equal to theta plus I'll call this angle as phi. This angle is phi. So in that case, because आपके पास अगर मैं ये ब्रेड बना लूँ, ये आपके पास एरिया वेक्टर है, और ये इसके साथ जो ब्रेड थी एक्चुअली, जो आपके पास ब्रेड थी, उनके बीच में जो एंगल है ये थीटा था, ये फाई हो गया. So therefore you can write theta plus phi is equal to theta plus phi, that will be equal to 90. So therefore what I'll do is that I'll go back to the expression which I have written, 90 So therefore, fine, I'll go to this. So therefore, I'll write torque can be therefore written as, I'll write torque therefore. I'm keeping the same color because so as to see that you have taken theta from that. You can write torque is equal to I A B cos of theta, because you know that theta plus phi is equal to 90. So you can write theta is equal to 90 minus phi, and you know that theta minus phi can also be written as sine of phi, AB sine of phi. So this is actually torque acting on a current carrying loop. And if say for example, if my coil is having, I have assumed that we are having only one turn. If I am taking n turns, then in that case we'll write torque is equal to n matlab number of turns in the coil, and that's I A B sine of phi. So this is my torque, and we are going to use it while explaining the working of galvanometer. So I'm going to use it in the galvanometer. For that, you'll remember this. I'll do that in the next video.